Hello, this is Dr. Han. I'll be doing the Lab 8 open loop, closed loop, and PID control. And this is the last lab of the semester, okay, after this week. And you can concentrate on doing your projects and studying for the final exam. So this is prepared for the ME 4234 at Texas Tech University. So, so before you start watching this video, I assumed you watched the lecture video and then read the assignment PDF and took and passed the homework, okay, assignment answer script. So we have these four elements for the lab, and the first one is a LabVIEW program installed on my computer. We have an amplifier, servo arm, and the National Instrument DAC. Okay, and if you want to look at it closely, okay, this is the arm, and then this one, okay, I just put the arm on top of the amplifier, so you see a part of the arm there, and this is the amplifier, and this is the DAC. So how does it work? This arm, okay, has encoder and the potentiometer, and we're only going to use potentiometer. So this is reporting the value of the the orientation, okay, orientation of the arm, okay. So orientation of the arm, how is it reported? It's a potentiometer, so it reports it as a voltage, okay. And your voltage, the 5 volt corresponds to 180 degrees, and negative 5 volt will correspond to negative 180 degrees. And then if you're curious about the angle, one second, how do I go back? Here we go. Okay, this is the zero line. This is 45-degree line. This is a negative 45-degree line. Okay. So at 45 degrees, can you do the math? What kind of voltage will it send out? Will the potentiometer send? So 180 degrees correspond to 5 volt, and 45 degrees will correspond to 1.25 volt. So, and then this signal, okay, is gonna go, this is the same wire right there, okay, go to the amplifier where it says analog sensors, and the same signal is gonna go to ADC, okay. And then this is, believe it or not, this one, okay, this is connected to, this has like four RCA type connectors, and one of them, okay, one of them is sending out the sensor data, and then that one, okay, is gonna be connected to, okay, it's connected to analog, which one, input or output, okay, input, right, it has to read the data, the DAC has to read the data, potentiometer data, location data, orientation data, and then this data is going to go to the computer, and the computer at LabVIEW is going to calculate what kind of voltage that you need to send out to the arm, okay. And how does that work? That value is going to go to a analog output right here, okay, right here, and then this is gonna go to amplifier command right there, and then that same signal, okay, I guess now you can provide more amp, right, okay. I mean that cannot have give you more than anything more than probably like point maybe 25 milliamp, okay. Now you can go to the load, which is the motor, okay, and it can send as much as 4 amp, okay, 4 amp, and this is gonna go out to the motor right there, okay. So there's no way you can make a mistake connecting these, because all the cables, they look very they're very specific for that, okay. So even though one cable, okay, two ends not gonna look the same, okay, so that way you don't make any mistakes. So let's see. Yeah, so this is the front panel, okay, of the LabVIEW program, and I think I made it into a movie so that you can see how wide that is. And then, and as you know, the LabVIEW, it's impossible to zoom in and zoom out, right? Yeah, so you can only scroll. So let's see, where's my mouse? Okay, here it is. Okay, I think I'm scrolling sideways to see what it looks like. So let me pause right there. So this one stands for, you put in the input. Okay, this is a block diagram, right? And then if this toggle switch is in the open loop position, this loop will be, feedback loop will be broken. Okay, broken, right? And if this is not the other position, then what? Then you have a feedback loop, right? You have a sensor data going back, okay, going back and comparing it. You're subtracting it from the input, okay. And then this is the compensator block. Okay, and then we put in some disturbance just to see how our PID controller can handle it. And it goes to the plant. So remember what the plant is? Plant is your alpha divided by s squared plus beta times s. Okay, that's the where this is the voltage, where this is the angle. Okay, but in this case, angle is measured as a voltage, right? So here, okay, and so I guess plant technically shouldn't have any units. Okay, it doesn't have any units. So let's see if we have actually more. Okay, toward the bottom. Oh, one thing I forgot to mention is that what kind of input types you can put in. If you look in here, it could be sinusoid, step, or ramp and hold. That means it just goes up linearly and then just hold the position there. Okay, and or none. Okay, you don't have to put in any. Okay, you can put none. So let's see. I want to see the bottom half. So the bottom half. So this is kind of useful. Oh, go back, go back. Okay, bottom half. No, this is going fast. That one, I want to pause. Okay, right there. Okay, so this one is a chart. This one shows um, the location. This shows the what kind of target green. Okay, what kind of target you want. What kind of position that you want your arm to follow. Okay, and output is the actual. It's a real position. Okay, it's a potentiometer data, and the input, and then this is the input voltage. Okay, when you think about it, they're all in voltage. Why? Because all the angles are not really not measured as degrees. It's in volt. Okay, and then this one is a graph of the same thing. Once you stop the code, okay, and or as you run it, this should be plotting. Okay, this should be plotting the exact same thing you plot here. Oopsie, I didn't mean that. Okay. Oh, I went backward. Okay, so part one of the lab is manual control. There are three parts. First one is the manual control, and second one is the open loop control, and the third one is a closed loop control, the or PID control. So manual control is the when we decide instead of having a programmed input type, what we're gonna do is we're gonna put the toggle switch to manual control. Okay, that means I get to decide on the what kind of voltage will to send to the motor. Okay, based on the target position of the arm. So I'll look at the target. Okay, um, and then I'll decide what kind of voltage to put in. Yeah, and the user controls a manual control to adjust the voltage level. It's plus minus 5 volt there. I cheated in the next video. Okay. I put in plus minus 1 because I need a finer control than plus minus 5 volt. So if you really put in 5 volt, I think it can just spin before I can react. So let's see. So task one, it's pretty much what I just said. Download VI and make sure to fix the DAG assist in the block diagram so that you map the correct port, input and output ports that you're using. So remember, like I'm using AI 1 and then AO 1. So let's see. The next one is a video of my attempt. So this is in default setting. I didn't change anything except that I made sure that this is a manual input. That means this one will become visible. Okay, it's all dark now, right? Okay, so that I can control this. If this isn't programmed input, okay, I can't. Okay, so there's a fundamental difference between the programmed input type and the manual input. So manual input is the actual voltage that I put in. So I'm controlling. Okay, with this, okay, I'm controlling the input voltage. Okay, where this type of input, programmed input type, that type of input is called a reference input. This is a target. This is the position that you want your arm to follow. Okay, does it make sense? So anyway, I tried. Okay, so what I did was I manipulated the voltage. So this value right there is same as the white. Okay, this is white. Okay, so I'm not really looking at the white line. I don't really care about how much voltage I put in because what I was trying to do was, okay, let me pause. Okay, what I was trying to do was, this is a target. Okay, this is my goal. Okay, and then I'm trying to make my arm, which is a red line, follow the green. And was I successful? See, in the beginning I didn't even start. I started right around here. Oh, I think it only worked for 2 seconds almost. See, okay. let's see. Yeah, I think I totally gave up like halfway through. From here, see, they're not even close. I couldn't do it. See, I waited about 3 seconds to go up. Anyway, sometimes our students will do this and then they can actually follow about maybe one cycle pretty well, one cycle, and then they figure, oh, it's so tiring afterwards. Okay, so now let's go to the next. Oh, okay, let me turn off the sound. Okay, so this is my. It was this was filmed at the same time, exact same time that I was filming the screen, the lab view screen. Oh, this is really bad. Okay, it's supposed to go about plus minus 72 degrees. I'm pretty sure 72 degrees about there. Oh yeah, I'm pretty sure I was late too. Okay, so I'm gonna have to show you another video, which is our last video. Actually, this is the last slide. I'm gonna have to skip over there. Okay, the reason being, okay, I wanna show you. Okay, I wanna show how when the machine does it. Okay, how great it is. Okay, let me see. How do I go to the very end? I'm thinking I have no idea. Um, do I go like this? Okay, let me show you the very last one. Okay, so this is the um, current slide. Here we go. Okay, so this is, look, I tested it before I started capturing the screen. So look, okay, I start the VI. Look, they're on top of each other. Okay, and then if you want to see the actual arm, it's a next video. This is actually the final video. Yeah, so this is when I was using the PID control. So you see the manual control is what block that because I can no longer control. And look at the type of voltage. Look at this. Look at this up and down, up and down. Look at this. Look at this. This is type of voltage you have to put in. Look at this. Okay, so that you have an exact match. Okay, so let's go to the next video. I'm not sure how to go to the next video. Here it is. So you ready? Okay, here it is. Okay, I think it starts from plus 72 degrees. I think it has to move to 72 degrees and it goes back and forth. Yeah, I think I only filmed before like maybe 2 cycles. See how great it is? Yeah, it's actually pretty hard. Okay, even if you try to make the arm go to let's say 45 degrees and just stop there, it's really hard to do. Okay, I wish you are here to take up my challenge. So let's see. Let's go back to my beginning videos. So there's only 36 videos. Okay, only 36. So where am I? So I showed you how much I failed. Okay, I was really bad at it. I actually asked my son to do it, who loves video games, who I think is just amazing at video games. But anyway, even he couldn't do it. Okay. So let's see. The part two is the open loop control, and this is inversion. We talked about inversion. What is it? So really, namely, what it is that you have a compensator, which is exactly the same as 1 over the plant. Okay, 1 over the plant. So what does that do? Okay, without the feedback loop. Okay, so you have no sensor. Okay, you're just really basically just doing it blind. So what you're doing in essence is you calculate the voltage that you need. Okay, based on the desired position. Okay, and you put the voltage in. Okay? The problem with that is that, well, do you really have the exact, do you really have the correct model? Is this really the plant alpha divided by s squared plus s times beta? I mean, did you get the correct numbers? How about initial conditions? I think the big problem we're having is that I keep forgetting to put the initial condition, the initial position, like 0 position. So I have an error to begin with. Okay, so when we actually implement this, okay, it's 1 over p. Okay, it's not a proper transfer function. What that means is the order of the numerator. Okay, what is that? Order of the numerator is s squared, and order of the denominator is a 0th power, right? So this is not proper. To be proper, it has to be least. Okay, the order has to be the same. Okay, so we do it in 2 parts. So make it proper by multiplying the top, multiplying the bottom by s. Okay, s, and then top and bottom by s. Okay, so you have in the numerator you have s squared, and take that s squared out, and then we gonna do this first, s plus beta divided by alpha times s in with the state space representation. Okay, and after that, what we're gonna do is multiply by square. So what does that mean in time domain? Multiply by a square. That means you differentiate it twice. Okay, so let's see. In the task, it says alpha is 80 and beta is 30. We need that value so that we can put in a. This is your state space model. This is your A, B, and this is your C and D. Okay, so beta is 30, alpha is 80, so this must be 0.375, and then 1 over 80, that's 0.0125. So remember those two numbers. So put those numbers in, and it says the turn the switch inversion on, programmed input on. Okay, I changed the name just for this presentation because there are two things called the programmed input. So I think automatic control might be maybe a better name for it. And then you get the servo arm to go to 0, position by hand, okay, and run the VI. Okay, so this is a video. So did I do all of that stuff? I put this one 0.375. Remember that? This is zero point 0, this is 1 over 80, this was like 30 over 80, and then put this one, it used to be called the programmed input, and I don't know, I thought the automatic control is a better name, but this one, whenever this is on, that means now you look at this, now the input comes from here. Okay, and this is set to sinusoid, and inversion is on. What that means is that you're gonna differentiate twice, okay, before it gets added to disturbance, and it goes through the plant. So this is still open loop. Why? Well, there's no feedback. Okay, there's no measurement. Okay, I mean we are capable of measuring, but we're not. Okay, we're not using the data. So let's see. Okay, how well does it do? So remember, what we're doing is we calculate. We know what kind of motion we want, right? So we have a desired motion here. Okay, and what we're gonna do is we're going to calculate the voltage that we will need to get that. Okay, so let's see. So let's look at this needle. So green needle. Okay, green is the target. Okay, that's what we want our blue needle to follow. Okay, blue is the current position, and then green is the target, and red is the voltage that it has to put in. Okay, and I think voltage that we have to put in might be sinusoid too. Yeah, so look at this. I mean, are they on top of each other? I don't think so. The blue and the green, are they? No, they're like offset a little bit. And if you look at the same thing, you see the same thing. So now the color scheme changed. Okay, your output, this is the arm. Okay, arm, this is the arm. So this used to be blue. This is the arm, and then this one is what? This one is the target. Okay, we want this red one, red flat to be on top of the green one, well, which is not. It's off. It's a little off by 1.5 volt. I don't know what is that. About like maybe 50 degrees or so. Yeah, I need a calculator. And then this, look at this. Look at this. This is the voltage that you put in. Okay, this is putting it, and look at how smooth it is, right? Why? Because our input is smooth. It's sinusoidal, right? Function. So of course you're gonna have a sinusoidal input voltage. Okay, this is a calculated voltage, right? Okay, from the differential equation. So let's see. It looks like it's having an offset. Okay, it's not quite following it, but you got the idea, right? I mean, it's got the same frequency. Okay, but just not. Imagine if you have a disturbance that won't work anymore. So now I went backward. Okay, going forward. How do I go forward? Like here we go. Okay, so part 3. So this is the closed loop and PID control. So what lesson have you learned so far? Well, manual control. Well, for extremely talented people, okay, you might be able to match, you might be able to follow the target, but it was extremely difficult. And not only that, you can't do it forever. Okay, if you're the, I mean, right, you can only do it for like maybe 5 minutes or so. Yeah, oh, not even, maybe 10 seconds. So, and then in the inversion, and then if you have anything that's unexpected, if you have some error in the model or disturbance, it just won't work at all. Okay, so now we have a closed loop PID control. If you remember the PID controller, what does it look like? The compensator looks like this. This is proportional part, integral part, and this is a derivative part, right? Remember, S is a derivative. That's what, whenever you multiply by S, you're taking a derivative. What about when you multiply by S, 1 over S, you're integrating, right? So that's why it's called the this is the integral part, this is a derivative part, and this is a proportional part. So we have the same problem actually when we try to combine these three terms. If you use a common denominator, you'll see the denominator has s, but where the numerator has s squared. So we just take out the derivative control for now, and then we just look at this one, okay? PI controller. So PI portion has a state space representation like this, okay? So when you, if I ask you what this is a transfer function of what, in terms of the variables you see in here, it's the output y over input u. Okay, you should make sure that this is the right representation, right state space model for this. So um, let me see. I'm going to try to remember this. This is 0, 1, ki and kp, and we have to add the derivative control, right? And the derivative control is just a simple differentiation. So kd times take the derivative of the signal and then combine it with this. Okay, combine it with the pi portion. Okay, so that's what we're gonna do. So typically kp, if you increase the kp, it speeds up the system response. Okay, in many cases it actually decreases the state error too. So kd is mainly used to decrease overshoot or oscillation. Oh, I misspelled that. Okay, and ki is included. Okay, I'm not saying increase or decrease, just ki, just having a ki can change the system type number. Okay, it can increase the system type by 1. Okay, so you can reject the constant disturbances or the track step command. Okay, so this is based on our system. So it is increased to speed up the rate at which the error is being removed. Okay. So for the design rules for our servo arm, okay, is I'm not saying it's a design rule for a car or anything like this, right? So for our servo arm, okay, where the system model is what was it? It was alpha divided by s squared plus beta times s. Okay. The given desired natural frequency omega n, will choose kp first. Okay, so where kp is omega n squared divided by alpha, and then you should look back at the lecture note, okay, where we have a closed loop characteristic root. Okay, that's where it's coming from. So the rule number 2 is if you have a desired damping ratio, you choose a kd according to it. Okay, so that kd equals this. So by this time you probably know you already decided on kp already. Okay, and then rule number 3, okay, this is about the integral controller. So if you won't have any desired time constant for removing steady state error, then you choose, okay, your kp, so that your ki, so that it's kp divided by the time. Where did it come from? You really should go back to the part we talk about the characteristic roots of the closed loop system. So integral action is stabilizing. That means if you can help it, you don't want to use a big value of ki, okay, in order to remove the steady state error quickly, right? So if you choose a tau to be too small, your ki will be big, okay, and then they tend to make the system unstable. Okay, so actually the roots of the cubic system, cubic polynomial, is actually very difficult to discuss, right? It's not like quadratic equation where it's easy to see what the root's gonna be like. The cubic equation is very difficult. Okay, so test number 3 goes like this. Okay, it says we'll first determine the ballpark numbers for the damping ratio and the natural frequency of the desired closed loop response. So calculate the damping ratio for one oscillation peak using equation 15, and I put the equation 15 for you. Okay, so this one I think I used it in the lecture too, where I think n was 5 or something. Okay, so find the damping ratio if you just want to have one oscillation, okay, before it settles down. So when you plug in 1, okay, I did this one already. Okay, when you plug in 1, when you calculate this, you should get zeta close to 0.4. Okay, 0.4. So now I want the rise time to be 0.1 second. Okay, so this is giving you an example of how do you find the desired zeta in omega n, because that's what it says in the previous slides, right? because the previous slide says how do you find the Kp, Ki, and Kd? Okay, so based on the desired zeta and omega natural frequency and the damping ratio. So that's what we're doing right now. Okay, so the initial criteria will be given. Okay, in terms of something like this, like a rise time, settling time, or one the the how many oscillations before it settles down. What else? The what is it? The MP, the overshoot, percent overshoot, right? So here it's given in terms of rise time and the one oscillation before it settles down, right? You wanted the one number of oscillations. So if you want the rise time to be zero point 0.1, we're gonna use this equation given right there. Okay, so I know zeta, so I plugged it in, and I found that my omega natural frequency is about 15.3. Okay, and then I think I did tell you about this formula, how the rise time formula is. Rise time is actually quite right. It's not a line, right? It's not proportional to zeta, right? Yeah, I think there was a graph that I showed in the lecture. I actually ran many cases and then figure out like how uh, um, they're related, rise time and the zeta, and it's not linear. Okay, but this is like pretty close. Okay, this is really not a bad approximation. So let's see. So to investigate what KP does, what do we claim that it did? Then we say that it speeds up the response, and I added that it tends to decrease the steady state error if you had any. So to to vary the KP, we're gonna modify our LabVIEW program. Yeah, so we're gonna make it be a little more challenging by setting the disturbance to be -1. Okay, and now we go back to closed loop. Okay, we turn off the inversion switch. That means don't no longer multiply by square. Okay, and then select the programmed input type to step. We're gonna do step instead of sinusoid, sinusoidal input, and then set the input select the programmed input. Sure, okay, don't do manual anymore. Okay, and then set DT to be 10 millisecond. Okay, so this is actually I tend to forget that one. Okay, this time I did it. Okay, so compute the proportional gain Kp for omega n is 15 using the rule 1 given on the previous slide. So I calculated, so this is a 15 squared divided by what was alpha? Was alpha 30 or 80? Let me see. It's 15 squared divided by, it was 80. Okay, alpha was 80. So the Kp is 2.81, and identify the matrices ABCs. You remember what it was? I do. Okay, so what did it say? Change this to step. Go to the programmed input here. It used to be called programmed input, but I thought the name was automatic control was better. Yeah. And then there was a 0, 1. Okay, I think we put in like really very small value of negative number. I think it tends to stabilize the system. Okay, but it was very close to 0. And C is 0. This was Ki 0. KD is 0, and this one was your KP. Okay, so it was a 0, 1, ABC was a 0, 1, KI, and KP. Okay, so and then make the open loop switch over to closed loop, and inversion now off. Okay, off, we put the disturbance in. Okay, so let's see. Is this a movie? Oh, yes, it is a movie. Okay, so already actually, you see the screen like this because I already tried it once before I start recording it. So let me see. Okay, so now I started it. So now this is 1 Mississippi, 2 Mississippi. At 2 Mississippi, what happened was it actually turned on. It sent the command at 2 seconds into it. Okay, it didn't just turn on right away. So, oh man. Okay, hang on. Pause. How do I pause? Okay. Oh, this is this good enough? Okay, this is good enough. Here it is. Okay, so I want to look at the time graph. What happened? I said arm go to 2-volt position. What's 2-volt? So 2-volt times 180 degrees and divide by 5-volt. Okay, they'll give you 72 degrees. It says arm go to 72 degrees. That's the command right there. Command came in. Okay, so the command came in in 2.01 second, 10 millisecond, right? So, and it came in right here. Okay, and then this is the voltage that was applied to the arm. This we actually have a 6-volt motor. Okay, we shouldn't put anything greater than 6-volt. So anyway, so when you look at the arm, what happened? It started from some negative position and went to a position that's slightly under. Okay, so I used to wonder about what is this negative position. So what happened was that to do this, okay, to do a step response, okay, we did the following. At time is equal to 0, we gave a command and says go to 0 volt position. Okay, but since we had a steady state error problem, it couldn't go to 0. Okay, 0 degrees. Okay, it went somewhere else. It went to like slightly negative. Okay, then then at 2 seconds, it said now go to 2 volt position, 72 degrees. Okay, it still couldn't. Okay, it had a steady state error. Okay, right there. Okay, so how do you feel at this table? So there is we took at this what's called the cursor legend. So this bar right here, yellow bar, okay, it tracks the output, where it's something called output. Output is the the current position. That's a red. Okay, so I can actually grab this and then move that around. Okay, and it tells you the time. This is x coordinate and then y coordinate. So that way I can actually read the data better, easier. Okay, easier. So next slide. Next slide. Here it is. So trial one. So this is just a screenshot of the previous page. Okay, just the relevant bit. So here, this is to show you this value right there. It's being read as a 2.37 and 1.5774. Okay, I mean, I believe it. Okay, it's better than me reading it, just zooming in and reading it myself. Okay, so it says that when you look at the table in the back, you're supposed to fill out this table for various values of KP. Okay, so KP equals, I don't know what happened to it. What was KP? 2.8 something, right? So when I put the KP equals 2.8 something, that's trial number one. So what's the rise time, overshoot, and settling time, and steady state error, and then stable and stable? Well, first of all, this is stable. Okay, why? Because when you look at the, when I mean, it was able to. Okay, it was able to go to some steady state position, right? Unstable system, what happens is that it keeps asking for more, bigger and bigger voltage input, like this white line right there. Okay, it's gonna keep going up until I put a physical limit. I mean, I put a ceiling to that. Okay, why? Because if the computer, okay, if your PID controllers keep asking for bigger and bigger voltage, and if I keep giving it to it, what will happen is that your motor will burn out. Okay, and this has happened. Actually, this has happened. I guess many times. I guess. Okay, so about three times over the last maybe 6 years. Okay, and then and finally I just had it. I fixed all the motors. So now we have all the working motors, but before we had like five broken ones. And then why were they broken? Well, because because somebody was playing around with the switch in the amplifier, and amplifier has something called a 3x. Okay, so whenever I say, oh, put in 3 volt, what it'll do is then you multiply 3 and it'll put in 9 volt. So sometimes, so right now, limitation of this was 6 volt. So it's 3 times 6. Well, it was putting in 18 volt. Okay, but that was the, and where I meant the maximum to be 6 volt. Okay, from the amplifier was giving 3 times that. Okay, why? Because somebody was just us, I guess students were like fiddling around with the knob. So anyway, no more. Okay, no more. The amplifier, it's been kind of fixed. What we did was we just put duct tape to so that people cannot adjust that setting. So anyhow, okay, I just want to go back to this one. So I was talking about stable, unstable, right? I can tell because look at this voltage. Okay, it didn't ask for the more and more and more and more, and then that will result in then unstable response. So here we go. Okay, so how about the steady state error? So what you do is I said go target was 2. Okay, it's always the reference minus the current. Okay, the target minus the actual value. So target was 2 volt minus 1.61, which is the steady state value. Okay, and then I just changed that to degrees. How? Multiply by, what was it, 180 degrees, and divide by 5 volt. Yeah, that should be 14 degrees. So when I tell it to go to 72 degrees, it was actually going to, I need a calculator. What's 72 minus 14? It was actually going to 58 degrees. Okay. And the settling time, it was a 2% settling time. So you look for the time when it becomes plus minus, within plus minus 2%. So here I can see that it's an underdamped system. So it never went over the steady state position, right? So your steady state position is 1.61 volt, right? So what I did was I take 1.61 and I multiply by 0.98, okay, instead of 1.02 because it didn't go over that value, right? So I look for when it was 1.5778, and I was really lucky. Look at that, okay? Right there, okay? 1.577, because its data is taken every 10 millisecond, right? So I might actually miss that value. So this is good enough. So, and then what was input given? What time is equal to 2? So I said settling time is 0.37 second. Okay, I'm not going to argue whether this is it really, should I subtract the first 10 millisecond, because when the command was given at 2 second, you actually got it, right? At 10 millisecond later, right? Well, I'm not going to argue. Okay, I'm just gonna say that as long as you use the same, okay, same method every time, okay, same way of calculating this every time, then I don't care, okay. So I'm going to just subtract 2 seconds instead of like 2.01 second from this time. So how about the overshoot? What, did it ever go over the steady state value? Okay, don't look at the target anymore, just look at its steady state value at 1.61. Did it ever go over that? No. Okay, so you have a 0% overshoot. So rise time is a tough one. Okay, rise time is, it's usually taken from 10 to 90%. Okay, so 10% of what though? Okay, so what I decided to do was I decided to go for the whole range. It starts from about negative point 0.2, right? Negative zero point 0.2 to 1.6. True. Okay, so total range is about 1.8. So what I did was, okay, how long did it take to get to 10% to 90%? Okay, so let's see. Okay, let's calculate the 90%. So you have 1.6. The total range is 1.6 plus zero point 0.2. Okay, what's 90%? It's like, oh, I don't think I did it right. Okay, 1 point, what did I say? 1.6 plus zero point 0.2. I think I should just do it in my head instead of using a calculator. Okay, so that's 1.8, and then I want to have the 90% of it, right? So that's 1.6 1.62. That's measured from the very bottom, okay? Very bottom, which is zero point 0.2. So subtract zero point 0.2, 1.42. So I found out when does it hit 1.42? Okay, 1.42. I said, oh, it's about 2.23 seconds. I use this the cursor legend, the tool. Okay, so 2.23 seconds. I don't know where that is, around here maybe. Okay, and the 10% is the 10% of the total range. Okay, I just look for the where is the 10% of the total range, somewhere here, and I looked at the time. Okay, so that was about 2.04 seconds. It's the 2.0. Oh, I can't even read this. So anyway, rise time was about 0.19 seconds. So you continue. This actually was quite boring. So you continue because we have like, I don't know, 10 trials or something. So I skipped the second one and I did the third one. Why? Third one actually has an overshoot. Okay? You have a steady state value of, I don't know, 1.89. I don't know what it is. Okay? But I wanted to show you the slides because I can see there's an overshoot. Why? Why? Because your steady state value is, okay, it goes over the steady state value and it comes down, right? So what's an overshoot? Overshoot is, it's defined slightly different from the ones that you learned in ME 3333. So overshoot there is that just x max minus x steady state. Okay, but that's a useless definition. You need to normalize it. So you divide by the steady state value. Okay, that's gonna be your overshoot, and if you want to make the percent overshoot, just multiply by 100%. Okay, so don't use a definition that says the overshoot is x max minus x steady state. Okay, that one really is useless. Okay, I mean you really should be, it should be at least written in terms of just a decimal, like, okay, like zero point 0.2 or something. Okay, or 20%, same thing. So let's see. I actually did all these trials, and I was sitting around at home. I was just doing all of it. I thought about just doing the first and the third, and then not even third. I was gonna just the first and then be done with it. But I decided if my students have to do it, I'll do it too. So then when you look at this, first two trials, I had no overshoot. Okay, and you can see the settling time, well, like getting shorter and smaller and smaller. Did it? For these two cases at least. Okay, and the steady state error was what it did, that definitely decrease, right? Okay, how about rise time? Rise time did decrease. Okay, so so is there any better way to study this? Of course, I love MATLAB. So I went to MATLAB simulations. So what I did was, I mean, I have an exact same model. I know my alpha, I know my beta, and then for this one, what I did was I vary my KP, 1, 2, 3, 4, 5 values. There used to be 5 values, but I think the fifth one was a little too big, and sometimes was making the response unstable. Maybe that was the point. Okay, but my heart couldn't take it. Just looking at the arm going back and forth like crazy, like putting in the maximum voltage in out there. So anyway, so I didn't like it, so I just took it out. I think now I realized I think it was meant to be unstable. So anyway, so here actually I put a slight small, very small Ki, and then this is as you increase your Kp, what happens? Your rise time definitely gets smaller and smaller, right? Do we find that? Yeah, it does get smaller. Maybe not in that last two. Maybe I couldn't tell. I mean, you saw how I was measuring my rise time, right? Okay, so um, they're all estimates. How about the overshoot? Overshoot. Okay, no overshoot, right? Okay, and then once you start having underdam system, what happened? Overshoot increases, right? So I think it's in the order of blue, green, and red. Okay, so what I did was I actually looked at the root locus because for me I think that's the best way to look at it. Look at how the transient response changes when you look at the root locus. Huh? When you vary the KP, it looks like this. So this is the part. This is the I think this is when you have a double root. Okay, the repeated root. This is this case right there. Okay, and then it moves along this distance. I mean along the vertical line. Okay, when 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 your system is underdamped. Okay, so what does that mean? What is underdamped system? When you have complex roots, right? Complex roots. So what does that mean? Okay, they have the same real part. What that means is that you have the same. What remember what the response looks like? Your response will have something like e to the negative zeta omega n t. So this is your zeta omega n. This is the real part, and then zeta omega n also controls what settling time, as I believe. Okay, so as long as they're under them, what happens is settling time becomes all the same. Okay, when they're overdamped, when the root is on the real axis, okay, dominant root will take over, right? So as the dominant root moves to the left, it becomes faster and faster and faster, and to up to a point, then what happens? And the roots will split, and then we'll have the same settling time. Okay, so initially you can actually your settling time could change, right? It got reduced. Then what happened? Okay, once it's underdamped, it doesn't change anymore. Okay, settling time will be the same. So root locus can explain. Okay, it can explain why. Okay, why change in response is a certain way. So this is a sample code that I use. If you want to try, you can copy this code and then try this. Okay, I was afraid I might have switched to alpha and beta because it took me probably 5 years to visualize memorize alpha is 80 and beta is 30. So this is my root locus plus. So where did this come from? This is our characters equation, and I want to see how the roots will change with the kp. So what I do is I lump everything else without the kp together, okay, right? This, okay, and divide by that, okay. So this will become 1, right? This whole thing divided by this plus the last term. So you're gonna have 1 plus now 80 times kp times s divided by, so that's 80 times kp times s divided by the other three terms, right? So sorry about the extra plus sign. So from here, okay, you just need to put in this transfer function right here. So I think I just made up my kd value to be something and ki to be something, okay, and then let me see, what did I use? I think I used kd 0 and ki I put in 1. I actually checked with when I put in ki equal to 0, the time history doesn't change that much. So anyway, this is just an extra information if you're wondering about this. So now we do the same thing by varying the kd. Okay, so kd is determined so that zeta is equal to zero point 0.6 using the rule 2. Okay, rule 2, and then use the value for the kp for omega n is equal to 30 and set the ki is equal to 0. Okay, so did you calculate what kd is? Should I wait for you? Okay, so kd if you calculate correctly, it should be 0.075. And KP, I think the third one, is 11.25. Was it the third one or fourth one? I just read it. Well, Kp that corresponds to omega n is equal to 30. So that's 30 squared divided by alpha. So that's 11.25. So you only change this number, okay? Because I think that was the last trial. So you only change Kd from 0 to that number. Is this the, okay, so that was the video. So here it is. So what did I do? I actually did them. I actually just, sat around, I ran these cases and read those values. Yeah, they're both stable, and the steady state error was, is it about the same or did it decrease? And setting time, it looks like it increased, overshoot. Um, it became underdamped. Yeah, and rise time is about the same. So really, really, for you to be able to figure this out, is I think it's a really best way to do it is to look at the root locus. This is a MATLAB simulation of those three cases. Okay, those three cases, and then this is in the direction of a increasing KD. Oh, I think I might have put these numbers wrong. Okay, I better fix that. Okay, it's a little too late now. Okay, so increasing the KD, so this is the first one is a blue, the second one is green, the third value is the red. Okay, as you increase the KD, kills the oscillation. Okay, and settling time seems to what? Increase. Did it happen? I only have two data. Okay, so it's really hard to tell. So I looked at the root locus. Yeah, root locus is really probably the best way to tell what happened to my root. So look at this. So these are my when the KD equals first value 0.075. Okay, and then when you increase KD, okay, what happened? It brought down the roots this way, right? Okay. So what does that mean? Okay, in terms of settling time, it should have settled a little slightly faster, right? Why? Because it pushed the real part of the root to the left. Real part is a negative zeta times omega n. That has to do with the settling time definition. Remember the settling time, 2% settling time was like 4 divided by zeta times omega n. So slightly, it pushed to the left. Okay? And what else? What else? When you look at this angle, okay, angle that it makes the horizontal axis, do you remember what that is? Okay, that has to do with the zeta, right? Damping ratio. So more vertical, the greater the angle, you have a smaller zeta, right? Smaller zeta. This line, right? If you draw a line like this from the origin to that star, okay, that angle. If this is 90 degrees, it's a neutrally stable system. That means it doesn't die, right? It doesn't decay. So this angle controls, okay, the zeta. So I think the relationship is cosine of that angle is zeta. Okay, so when angle is 0, that means zeta is equal to 1, right? It's critically damped, right? So what happened to the angle? It becomes smaller and smaller. That means you're further and further away from the vertical. That means you're more damped, right? That means it controls the damping. Okay, damping ratio controls what? The what is it? The overshoot, right? So it decreases the overshoot. So overshoot decreased. Okay, decreased. Sorry, I think I really made a mistake with that one. Okay, I don't think that's correct. So now, and something funky happens. If you increase KD even more, what happens is now it's going to move along the x-axis, and the opposite will happen. Because why? This is one of the root. This is second. You have three roots, okay, and then the other ones you can't see because I didn't zoom in enough. I didn't zoom out enough. So I have another root, okay, two other roots somewhere. This is a third order system. So for every color, you should have three roots, okay. So you can't really see another one. But anyway, look at this red one. What happened? One of them moved to the right, making the system really slow, right? When the real part is closer to 0, it's a very slow route, so it's not dying as fast. Yeah? So it is actually a lot more complicated than the rules that I showed you in the beginning, where how the KP will do this and KD will do this and then, okay? So it's hard to say, okay? It depending on where on root locus you're moving. So now effect of varying Ki. So now what we're going to do is we're going to decide the Ki using the formula where So remember, these formulas are what? Based on what? The assumption that ki is small, right? And then where the third order equation can be written as the second order polynomial times the first order polynomial, right? That, I mean, didn't you feel like it was totally made up? And then it was, we had a condition where the ki had to be small. So now compute the ki using the third formula, which was I must say I can't remember what that is. So should we look at it quickly? Okay. How do I go? How do I go back? What's the formula? Can't do anything without the formula. Oh, here it is. Okay. So your ki equals kp divided by the time that you want. Okay. Time. Um, this is time it takes for the error to be removed, something like that. Okay. So where am I? I think I was here. Okay, so Kp for omega n equals to 30 was, I think it was like 11 point something, and then now and then we're gonna use the Kd for the zeta is equal to zero point 0.9. That was the second case, and we're gonna use a tau I. So now, okay, see if you can calculate what Ki is. I'm gonna show it to you in the next video. Not next video, next slide. Did you calculate 37.5? I think that's the second trial. The first one should have been 11.25 and the second one is 37.5. Did you get that? So I actually sat around and then did this one too. The rise time seems to be the same, settling time they seem to be the same, status error seem to be 0. Okay, only thing that changed seems to be the overshoot. Okay, so let's see what happened. Okay, oof, this is complicated. Okay, so for these three cases, this is blue, green, and red in that order. Okay, in increasing ki, what happened when you increase ki? You definitely increase the you're increasing the overshoot. Okay, meaning your zeta is decreasing. You're becoming more and more underdamped system, right? More. So now, when you look at the root locus, it moves from blue, okay, three roots, these three roots. And the second one, it moved to the left. Okay, what happened? Okay, look at the vertical. Look at the horizontal location. Okay, because that's what controls the settling time. They're about the same. Okay, I really couldn't tell when I look at the blue and the green. The red, I think there's nothing dramatic. Okay, in fact, it looks like it moves. The roots move to the left and right again. Right. So so that's what I mean. It's like really PID, the third order system, third order roots, very difficult to tell. Okay, what's gonna happen? So this is the when KD was point 0.3. I think it's supposed to be point 0.3, maybe. I don't remember. Okay, so I'm having trouble remembering all the numbers. So now, okay, finally, what we're gonna do is let's see how good our PID controller is, because what was the goal in the from the beginning? I want to have a target motion. I want to have a target position for the for our arm, and except it's not a steady state it's not a constant position. I want it to be following a sinusoidal function, right? I want it to go back and forth, plus and minus 2 volts, plus minus 72 degrees. So if you use these values, how good will that be? And then you already saw this video. I'm going to show it to you again and then see if you can admire it again. Okay, I still can get over it. How exact? Okay, I'm starting the program. How, look at this, they're right on top of each other. And then this one, I actually didn't even use the big value of ki. I used the first value, 11.25 instead of 37.5 or something. Okay, look how great it is. Okay, so in the beginning, when you look at it in the beginning, look. Okay, the red line was the initial position. It was at negative 2 degrees. Oh, I think I must put them in the wrong place. Like I put them in the negative 72 degrees instead of 72 degrees. I mean, it would have been better if I put it in 72 degrees. But anyway, so anyway, look, okay? Look, it had to go all the way from negative 72 to positive, a little more than 72 degrees, right? Okay, in what? About 0.3 second. And after that, it just pretty much just followed our position. Okay, the target really well. Okay, you don't want to look at this again, right? Okay, okay, next video. Okay, next video, would you like to watch this again? Okay. Oh, wait a minute. Oh, this wasn't taken at the same time as when I got the screenshot, by the way. Okay, if you see any discrepancies, okay, it's because it wasn't recorded at the same time. Okay, so this one looks like I actually zeroed it at time equal to 0. Look how beautiful that was. See, but the thing is, the arm is great, but the thing is, I think what I'm really astonished about is that plot right there. Okay, so I showed this to middle schoolers when we do meet Emmy. What do you think? Do you think they're impressed? No, they're not impressed at all. So I'm impressed. I thought this was a great lab, but so I decided to go with our two-story building lab. That one they really love because it's first of all it's very loud. Number two, we do have an emergency stop, and people just love looking at the emergency stop, and then they love it when I just use it, right? Because sometimes when I have a second mode, the vibration can be really loud. So anyway, so this is the this is the last of our lab, okay? And then there will be no more lab. And next week, you should have a self-learning project number three, which is about motors. So it's gonna be about servos and what's it servo? Servo, and then DC motor and stepper motor. Okay, then stepper motor. A lot of you will be using stepper motor for many different things like your projects or your design project, control project, whatever have you. Okay, and then some people like love just a stepper motor. Okay, so and then there's an excellent video that put up there which was made by me. Okay, so and I watched it the whole thing. I watched the whole thing and I just love that video too. So I hope you love it too. Okay, anyway, this is the end. I'll talk to you again to review the final exam. Okay, thank you. Okay, bye bye. Stop.